So we did a straight wire, and now we're going to do a wire that's in a circle. And so let me just give an example with this one. Right? You can see this is just a circular loop of wire, and so there's current running around it. Maybe there's a battery tucked in there somewhere, so it's producing the current. But anyway, it's just a current I that's going around in a circle. And what this is talking about is the magnetic field at the center. So it's saying, look, what is B at the center? And usually we'll approximate that it's anywhere inside, but really this is just for the very center loop. Notice it looks very much like the magnetic field near a parallel wire, except there's a pi missing in the denominator, right? For a straight wire, it would be mu naught I over 2 pi r. For the center of a loop, it's bigger because there's not a pi in the denominator. And you can sort of see that from this. If I take this wire and have it straight, versus if I curve it into a loop, if it was straight, the magnetic field would be the same all along there. So on this side, it would be pointing up, right? And when I put it in a circle, I kind of put all that stuff in the middle together. And so I increase the magnetic field inside the circle by kind of looping all of that part together a little bit. And so it gives me you can sort of see that maybe that it gives you a larger magnetic field. And so there's an example here that says, so that's my formula, right? And that gives me the magnetic field here. And so I can say, so here's an example for the loop, magnetic field due to a loop, and it says the magnetic field of a proton is approximately given by a circular loop of radius 0.65 times 10 to the minus 15 meters with a current of 1.05 times 10 to the fourth amps. So you've heard of maybe a proton spin. Some atomic particles have spin, and so which produces their magnetic field, and rotating objects with a charge distribution of some kind can be approximated as currents. And so I can calculate the magnetic field here just using that formula, B equals mu naught I over 2R, and that's 4 pi times 10 to the minus 7 Tesla meters per ampere times 1.05 times 10 to the fourth amperes divided by 2 times 0.65 times 10 to the minus 15th meters. That's a huge current and a tiny radius, right? And so what I get for this is about 10 to the 13th Tesla. And so it's a ginormous magnetic field if you're very, very, very close to a proton, right? So here are a couple of examples, just of slightly more complicated things that we could talk about. The magnetic field due to a closely spaced coil. So we just did a single loop, and we said, look, the magnetic field at the center of a loop is just B equals mu naught I over 2R. Well, if instead of a single loop, you have a whole bunch of loops just right there on top of each other, like a bicycle wheel looking thing, right? Then you just multiply by the number of loops you have, the number of turns, and that gives you a magnetic field. So it's just, it's just the same thing as N times mu naught I over 2R, right? It's just that many turns. Since the current that goes through one has to go through all of them, the magnetic field just multiplies. There's a different device called a solenoid, and you'll sometimes see that in car starters. And instead of having just a bicycle wheel looking thing where all the coils are in one spot, they're spread out long. And she might have 1,000 turns, but it might be a foot long. And so here we define this little n as the total number of turns divided by the total length. So there might be 1,000 turns here, and this might be 10 centimeters long. So you'd have 1,000 over 10 centimeters, or 10,000 turns per meter, or something like that, right? For those cases, the magnetic field at the center, again, so this is along the axis inside the solenoid, is B equals mu naught Ni, where N is the turns per unit length, we call that. So in this problem, we're asking the question, what's the magnetic field on the axis of a solenoid that has 750 turns over a length of 0.15 meters and is carrying 7 amps? And so if we break this down, we say, look, number of turns is big N, the length is 0.15 meters, and the current is 7 amps. And so we can go to our solenoid formula, B equals mu naught Ni. And so it's 4 pi times 10 to the minus 7 Tesla meters per ampere times 5,000 terms per meter times 7 amps. And so the amps and the meters cancel. I get units of Tesla. And what I get for this is 0.044 Tesla. Notice that if this is my coil, right, and my current's going this way, I mean, I'm looking down the axis of the solenoid, right? Then if I look at any individual wire, if my current's going this way, no matter where I grab the wire, if I point in the direction of the current, inside the magnetic field is coming out. And so I would say B is it's out of the whiteboard, right? If the current was going the other way, it would be into the whiteboard in the middle, right? You can just use the second right-hand rule and grab the wire with your thumb pointing towards the current, and your fingers will tell you which way the magnetic field is going. So it would be down on the, it would be in on the outside of the wire and out on the inside of the wire.